So, of course, using dots to represent electrons is a drastic oversimplification. And yet it's still useful, thank goodness. So one of the things that is lost is that electrons are not always shared equally. You probably have experienced this with other people. Someone that you're sharing a bed with, you have to share the blankets and share the space in the bed. Yeah, a couple of chuckles because that doesn't always go very well. Sharing a toy, sharing a piece of cake, oftentimes it's not equal sharing and yet it's still sharing. So that happens with electrons as well. So when we have a covalent bond where the electrons are not shared equally, it's called a polar covalent bond. What does the word polar make you think of? Polar bears, Polar Express, the North Pole, right? So our planet has a North Pole and a South Pole, and what's different about them? Yeah, it's a magnetic field, right? So there's a difference between one pole and the other pole. And that's the same use of the word here, polar bond. One end of the bond is different than the other end. But here it's not a magnetic field, it's electrical charge. So here we have an illustration of a hydrogen fluoride molecule. This is the hydrogen, and this is the fluorine. And when these two atoms share electrons, they don't share them equally, because fluorine is more attractive to the electrons, or you could say fluorine is an electron hog. He hogs all the blankets, right? He steals them. So if the two electrons that are being shared here spend more time over around the fluorine, then this end of the bond is going to be a little bit negative, and this end is going to be a little bit positive, right? It's not an ionic compound. It's not a hydrogen ion and a fluoride ion. They're sharing the electrons, but not equally. So we have a couple of ways of representing that. We can write, what color am I using? Let's do a different color. We can use this lowercase Greek delta. Capital delta meant difference, change in, final minus initial. This is a lowercase Greek delta, is sort of like a teenage D. It's kind of slumped over because it's looking at its phone or something. So this is partially negative. We use this to represent a partial charge. And this is partial positive charge. It's not plus 1 and minus 1. It might be plus 0.2 and minus 0.2. It's a little bit, but that can be significant. Another way we can represent this is with an arrow. The arrow points to the negative end, and just sort of to reinforce that and make sure we don't just think it's a regular arrow, make the other end into a plus. And we can observe the effects of this if hydrogen fluoride is a gas at room temperature. And so if we were able to observe the particles, the molecules, here's the negative and positive, and they would just be randomly distributed in space. If we apply an electric field here with a positively charged plate and a negatively charged plate, all of these molecules will swivel to line up, so the partial positive is lined up with the negative charge because it's attracted, and the partial negative end is attracted to the positively charged plate, and they all just swivel and line up, much like the needle on a compass, right? You can turn it around and stuff, and then you stop, and it just points north, right? So that's what these little molecules are doing. I have an analogy for this. This is one of my favorite analogies. So I've told you before, I think of electrons as being a lot like little boys, grade school boys. And so here we have two families. There's the fluorine family and the hydrogen family. And they are each sending out a little boy to play, and the two boys are friends, and so they're playing together. And where do they spend most of their time? Well, it kind of depends on what kind of homes they come from, right? So the hydrogen home, very loving parents, but very modest income. So they've got a black and white television. They don't have cable or anything. They've got a VCR and some old Thomas the Tank Engine videos. That's about all they've got. It's kind of sad, but it works. And if you're hungry, Mom will give you some bread with butter and tap water. They don't even have an ice maker. Yeah, it is all you need. It's, the basics, right? It's a good place, safe place. And then there's Florine's house. Florine has a swimming pool with a diving board and a slide in the backyard, trampoline. They've got the big screen TV, all the cable channels, every game system known to man. In the kitchen, they actually have a soda fountain. In the kitchen! If you just mention food or, oh, I might be hungry, Mom will order you a pizza delivered in. Right? So where are those two little boys going to spend more time? At Florine's house. Why? Because it's cooler. It's more attractive to them. Okay? So these electrons that are shared in this bond spend more time around the fluorine atom because the fluorine atom is more attractive to the electrons. And this arrow business, I think of, Dad comes home and one of the neighbors is out mowing the lawn. Could be either Dad. Dad comes home, hey, where are the boys right now? And the neighbor points at Florine's house, right? That's where they are. They're over there. Doesn't even need to think about it. They're there. Yes?
So can we think about it as along nuclear charge, that overall effect?
Well, it does have to do with effective nuclear charge, but it also has to do with size. And so the concept here is called electronegativity. You guys are getting really good at leading me into the next topic. So thanks for that. Electronegativity. So the definition of this is the ability of an atom to attract electrons to itself in a chemical bond. And it's generally inversely related to atomic size. So this is another one of those atomic trends, the periodic trends. So if we look at this, here we have one of those three-dimensional bar graph things. Here's fluorine over here. Fluorine is the most electronegative. So that is the coolest house imaginable for little boys to play at. And it's literally all downhill from there. Whichever direction you go, the next house over, further, is less and less attractive to electrons. Now, hydrogen over here has got to be a bit of an exception. He's got to stand out among the neighbors. So I probably exaggerated hydrogen's situation because obviously places like scandium are less attractive than hydrogen. So the general trend then is as you go across, electronegativity increases, the opposite of size. As you go across, the size decreases. As you go down a group, electronegativity decreases, size increases. Okay? Now, you may or may not have noticed that group 8A is not even on this table. It ends with fluorine, and these noble gases aren't even on there. Noble gases are so unreactive, they pretty much do not form compounds, so we just leave them off. They're happy in and of themselves. They just don't play with other people, right? They play by themselves because they're noble, right? And the noble children can't mix with the commoners, so that they're not even on this chart. Any questions? So there are numbers here, and electronegativity is quantified. It's got a number associated with it. It's kind of like a grade point system where 4 is the highest. So fluorine is a 4.0, and then everybody's down from that. And that was sort of, the person who discovered it said, well, I'm going to use a scale of 0 to 4. So there it is. Now, we're not really going to do much with the actual numbers. What's more important is that you have the trend in mind, okay? So we should be able to do something like this, arrange these elements in order of decreasing electronegativity: phosphorus, sodium, nitrogen, and aluminum. And so here, multiple choice, and the greater than, less than sign helps us to understand what decreasing electronegativity means. It means that the first one has the highest electronegativity, and they get smaller and smaller and smaller. So to answer this question, we need to find these elements in the periodic table. So there's phosphorus and nitrogen and aluminum and sodium. Yeah. Yes, it is the opposite of the metallic character, and it's opposite of atomic size. So we could go and look at the table in the previous slide and look at the numbers. Don't do that. The way I would approach this, I say, okay, well, here's fluorine. Who's closest? Nitrogen. So nitrogen is the closest, because same row, and there's nobody else in this row. So nitrogen's the highest. So that kind of just nails it, actually. Let's check the rest of them, though. So there's nitrogen, and the next closest would be phosphorus, and then aluminum, and then sodium. So nitrogen, phosphorus, aluminum, sodium. So the order of those elements would be the same for atomic size, metallic character, it would be either that way or reversed, or ionization energy, any of those. Any questions? Electronegativity is one of the more important trends to know, especially if you're going on to take organic chemistry, because just having this general idea of who's more electronegative becomes more important there. Okay, so bond polarity. A polar covalent bond is one where electrons are shared but unequally. And then at one extreme, we have the ionic bond where electrons were transferred. This is where, I guess, that one family is so badly off that the wealthy family actually adopts the child, right? So he goes and lives with them permanently. Here we have a pure covalent, I prefer the term nonpolar covalent bond. This is where the electrons are shared equally, because both of these atoms have equal amount of attraction. So this could be like two fluorine atoms, both super cool, but equal, right? Or they could be in the middle, or they could be hydrogen, right? We're not very attractive to the children, but they're both the same, so they're going to share equally, right? There's not specific categories for these. Much like many things in life, there's a continuum from this extreme to that extreme. And so we can use electronegativity difference, symbolized as delta En for electronegativity, because it's a long word and we don't like writing it out. We can look at the electronegativity difference between the two atoms and put them into categories based on that. These divisions here are arbitrary. It's what scientists decided on. So if the difference is between 0 and 0.4, so there could be a little difference, we still say it's nonpolar. If the difference in electronegativities is between 0.4 and 2, we say, well, that's a polar covalent bond. If it's above 2, we say it's ionic. We can measure the bond polarity. It's measured with dipole moment, which sounds like a senior moment or something. But it's a dipole moment, and that has the symbol mu. And you could have a dipole moment anytime there's a separation of positive and negative charge. So this gets used in other places as well. And I'm just going to describe to you what this is. We're not actually going to do calculations with it, but we may refer to dipole moment, and so you just need to know what it is. So it's defined as the charge magnitude times the distance between the two charges. That's the dipole moment. So if the charges are larger, the dipole moment is larger, or if the distance between the charges is larger, that makes the dipole moment greater. And the unit here is Dubai, not the country, Dubai, Dubai, and it's a very small amount of coulometers. So that's just also you've heard of it. So in this table we have bond types and electronegativity difference. So for a covalent bond, and I would add nonpolar in front of that. So a nonpolar covalent bond, we have a small electronegativity difference. A polar covalent bond, we have an intermediate difference, and if there's a large difference, we have an ionic bond. So I'm going to tell you what I want you to know so that we don't actually have to subtract electronegativities. There will be no subtracting electronegativities on an exam. There might be some of that in a homework assignment, but you can go look it up in the table. So a nonpolar bond. If we have two identical nonmetal elements. So the example here is Cl2. Two chlorine atoms, they're both chlorine, they have to have the same electronegativity, right? Now, is it possible to have a nonpolar covalent bond between two dissimilar elements? Yes, it is. There's one that I want you to know about. A carbon-hydrogen bond. The electronegativity difference there is 0.4, and so it's right on the edge, but it's considered a nonpolar bond. That's important because that one comes up a lot in OChem. A polar covalent bond. If you see two different nonmetals, I expect you to tell me it's polar. If I remember correctly, it's something like nitrogen and chlorine have the same electronegativity, so technically their bond is nonpolar. But without a table, I expect you to tell me that any bond between two non-similars, two different nonmetals, is polar. Yes?
Besides carbon and hydrogen, are the nonpolar covalent bonds all going to be diatomic elements?
Well, they're not. They include the diatomic elements, but they also would include bonds between the same element in a compound. Let's just run back to that table real quick. Yeah, you see nitrogen and chlorine? They're both 3.0. Carbon and sulfur, 2.5. So there are other combinations where you would have a polar bond even though the elements are not the same. I don't want you to worry about those exceptions. So what I'm giving you is a guideline that this is going to be good enough for what you need. And then a large difference would be two nonmetals. Two metal, nonmetal. What am I saying? And that falls into what we learned back in chapter 3. You've got a metal and something else. It's an ionic compound. So any questions? Another way to quantify stuff is to talk about the percent ionic character. So as with any percent, it's the part divided by the whole. So here it's the ratio of the bond's actual dipole moment to the dipole moment it would have if the electron was completely transferred. So if the dipole moment is the same as what would happen if the electron was completely transferred, then you'd have 100% ionic character. So it turns out that no bonds are 100% ionic. They're just, pretty close. So this this graph is showing us percent ionic character versus difference in electronegativity between the two elements. And so we see some of these up here, potassium chloride, lithium fluoride, potassium fluoride. They're up around 80, 85% ionic character. And so what we say is that anything that's over 50% ionic character is considered an ionic bond. So that's one of those little lies we tell you. Oh, an ionic bond is where the electron is completely transferred and they're two separate things and then they're attracted to each other. Well, it turns out that the family of origin has some visiting privileges, visitation rights, and they actually do share a little bit. So that's a detail that we tend to gloss over. If you look at these compounds up here, though, all of these that are above 50% are metal-nonmetal combinations. And then we have this one over here, kind of with this cluster, but under the 50% mark, hydrogen fluoride. Because hydrogen and fluorine are both nonmetals. And so this qualifies as a covalent bond. And we see a lot of the other diatomic compounds here, and their percent ionic character is much lower. But they're still on there. And so something like H2 would have 0% ionic character because it would also have 0 electronegativity difference. So any questions? So this is this is a skill we definitely need to have. Determine whether the bond formed between each pair of atoms is, I keep meaning to change this slide, nonpolar covalent, polar covalent, or ionic. So between iodine and iodine, that's going to be pure or nonpolar covalent, right? Because iodine has the same electronegativity as iodine, right? So there's no difference. How about the bond between cesium and bromine? It's going to be ionic. How do we know that? The cesium is a metal, right? And I think we all recognize now, we don't just look at the element name and like iron, oh, that's a metal. Cesium, no, I don't remember seeing any cesium metal. You look on the periodic table and find it, right? And it's way over there, it's definitely a metal. So that's an ionic bond. Phosphorus and oxygen, polar covalent. Two nonmetals, it's a covalent bond. They're going to share electrons, but they're not the same. And I'm not going to try to trick you on an exam or anything where I give you something like, nitrogen and chlorine where their electronegativities are the same. Because there are situations like that, but they are exceptions. But like I said, the one thing I do want you to know is carbon-hydrogen, that's a nonpolar covalent bond. Any questions about this one?